Okay. So let's start with this, maybe. Okay, and then we'll look at the second. So part A, we have a finite game. A strategy Si of agent I is strictly dominated in the mixed extension game. Well, this is actually the normal definition of strict domination. Nothing fancy here. But the important part is this, which it says, so normally when you check for strict domination, you have to check for every strategy. So you have to check that there is a strategy of player I, mu I, which yields a higher expected utility, expected payoff, okay, than SI does, no matter which strategy, in this case, mixed strategy profile, the opponent plays, okay? So that's a pretty large set to check if mu I yields a higher expected payoff against SI given mu minus I. But what this statement says is that you don't have to check over all mixed strategies. You only have to check against pure strategy profiles of the opponents, okay? So it simplifies the task of checking for strict domination quite a bit, okay? So it's a nice statement, a nice proposition in that sense. So it's an if and only if statement, so we have to show two directions. Whenever this is true, we have to show that this is true. And whenever this is true, we have to show that this is true, okay? So it's a two-sided. So we'll start from this direction. That is, if this statement is true, then the statement is true, okay? So we're given that, assume there exists player I has a mixed strategy, okay, such that no matter which mixed strategy his opponent plays, no mixed strategy profile, I'll just write it simply as J different than I. No matter which mixed strategy profile his opponents plays, the expected payoff he gets by playing mu I, given that the opponents play mu minus I, is greater than the expected payoff that player I gets, given that he's playing when he plays SI and his opponents plays mu minus I. Okay? So this is what we have. What we want to show is, for any S minus I in capital S minus I, the expected utility that he gets from mu I when the opponent plays mu minus I is greater than the expected utility that he gets when he plays SI and his opponent plays S minus I. Okay? So that's what I want to show. How do you show it? Yep.
Is also included in mu minus I.
Exactly, right?
S minus I is played with probability 1.
Okay.
Works for
everything. So actually, this part is pretty trivial. So, well, I'll first state it in a weak sense, in a bit hand-waving sense. So we said any pure strategy in, again, quotations, is a subset of the mixed strategies, okay? That is what we said was, for every pure strategy, there exists a mixed strategy, okay, which selects that pure strategy with probability 1 and any other strategy with probability 0. So in that sense, this set is a subset of this set. Well, if this statement is true for any element in this set, it will also be true for the subset. And that's it, actually. Okay? That's the whole thing. Okay? Since since I'll write this in quotation, Sj is a subset, well, maybe I should put the quotation here, of, okay, since this is the case, this statement star implies, let me call this double star. Okay, that's it. That was the easy part. So the harder part is, how do we go from here to here? So we start by assume that for any s minus I in capital S minus I, ui s minus I is greater than ui si s minus I. Okay, so want to show that this is the case. Okay, well, we don't have to worry about that. We're already given mu I. Okay, so we want to show that if this is true, this part has to be true. So how do we do that? Let me put this away for now. So how do we do that? Well, so that's what we want to show. That's a universal statement on mu minus I. So I'll start by saying let mu minus I be a mixed strategy profile of the opponents of agent I. Okay? So I took a strategy profile, a mixed strategy profile of the other agents from this set. So that's what I want to show. So what do I do? Well, this is what we have. Okay? So what does that imply? Well, for any S minus I in capital S minus I, okay, what do we have? Let me write this part first. First, let me introduce a piece of notation. Let mu minus I, S minus I denote the product of mu j, Sj, j different than I. So I don't want to write this long expression every time. I'll denote that with this short notation. Okay. So this will be the case if mu minus I, S minus I is greater than 0. So if this is the case, then we have this. If mu minus I, S minus I is equal to 0, then what do we have? Then we have equality. Yep.
If we sum over S minus I, then we will have strict inequality.
Okay, so how do we know that's going to be strict inequality?
Because we know that at least one of them is greater.
Exactly. Okay, so the opponent is going to play at least one strategy profile. So for at least one strategy profile, we have to have this condition. Okay. That's UI SI. So that's what we had. That's what I sort of.
S minus I, mu minus I.
Oh, here, there's the minus. Yes.
Line upper side, you go to left.
Mm-hmm.
Is it SG?
Oh, J. Yeah. Okay. Yep.
Now, mu minus I of S minus I is greater than 0 means that the probability assigned is greater.
So the strategy profile S minus I is played with some positive probability by the opponents of agent I. Okay? So if I multiply, so what we have is, we have this, so let me call that double star implies this condition, okay? So from double star, we have this condition. Multiply both sides by a positive number, the inequality doesn't change. But this number could also be 0. But then if I multiply both sides by 0, I will get equality, okay? Since mu minus I, S minus I is positive for some S minus I in capital S minus I, thereby the above statements imply, well, as your friend said, it's either positive or equal to 0. So we either have terms like this or terms like this. Add them up. Summation mu minus I, S minus I, capital UI, mu I, S minus I, greater than summation mu minus I, S minus I, minus I, so where the summation is taken over, S minus I. But what is this? This is the expected payoff that agent I would get if he plays the mixed strategy mu I and his opponent played the mixed strategy mu minus I. This is the expected payoff that agent I would get if he plays SI and his opponent plays the mixed strategy mu minus, the mixed strategy profile mu minus I. And that's it. Okay? That's it. All you use is just the definition of expected payoff. That finishes the proof of part A. Any questions? So we can finish it by saying quite easily done. Okay? Any questions? Could you please sign and pass it around? So, part B, if a strategy SI is strictly dominated in the game gamma, then so is any mixed strategy that assigns a positive probability to SI. So, what do we have? For any SI in capital I, so let me write that in the language of mathematics. For any SI in capital SI, for any agent I, I'll drop that part. If SI is strictly dominated in the mixed extension game, implies that for any mixed strategy of player I, for any mixed strategy of player I, if mu I of SI is greater than 0, then mu I is strictly dominated in the mixed extension game. So that's what we're asked to show, okay? So we'll start the proof. Let SI in capital SI be strictly dominated strategy of agent I in the mixed extension game. Okay. So what does that imply? Well, from condition 1, it implies either this or this. You can use whichever one, but let's use the definition, regular definition. Thus, because it is strictly dominated, there is a mixed strategy of player I. So I'll use mu I prime this time because I have mu I here. Thus, there exists mu I prime, a mixed strategy of player I, such that for any mixed strategy profile of the opponents, the expected payoff of agent I that he gets under the profile mu I mu minus I is greater than the expected payoff that agent I gets when he plays Si and the opponents play mu minus I. So that's what we have. Okay, so the hypothesis part implies this. So I want to show this part. So again, we'll do a direct proof. So that's a universal quantifier on I. So I say pick an arbitrary mixed strategy of player I. Okay. Pick an arbitrary mixed strategy of player I for which the hypothesis part of this statement, the second statement, is true. Be such that mu I Si is greater than or equal to 0. Again, what is this Si? Si is the strategy that we picked at the beginning. Si is the strategy that is strictly dominated. Okay? So, again, not to get lost, it's a good idea to write down what you want to arrive to. Yeah, okay. So what do we want to show? Want to show that mu I is strictly dominated, okay? Which means that there exists mu I double prime mixed strategy of player I, okay, such that for any mixed strategy profile of the opponents, we have the expected payoff of agent I from the profile mu I double prime mu minus I is greater than the expected payoff of agent I from the profile mu I mu minus I. So that's what we want to show. Yep.
Because we know that
So you're working with another pure strategy. So you're saying that there is another pure strategy, Si double prime, that strictly dominates Si. So how did we get to that conclusion?
since we know that UI prime
So,
at the definition there, mu I prime.
so there's a mu I prime, which strictly dominates. Okay.
But we know that it's a complex combination of mu I, Si, mu minus I for any. But we know that just convex combination is smaller or equal than the maximum pure strategy is played. Then to the maximum of the
So,
is double prime.
so your friend claims that this statement implies this statement, Si prime strictly okay. You object to that? Okay, let's give everybody a little time to think about it. Is the statement true? So this statement, okay, this statement implies this statement. That's what your friend claims. And another friend claims that. That's not true. So let's give everybody 2 minutes to think, and then we'll take votes. Do you have a question, or are you going to answer? Okay.
Shouldn't it be mu I prime?
Oh, yes, there's the prime here. Yeah. Yeah, that's the prime. That's without prime. Thank you. Okay, so well, so how many say the statement is true? That is, this statement, the fact that mu I prime strictly dominates Si implies there is an Si double prime, a pure strategy of agent I, which strictly dominates the strategy Si in the original game. How many think it's true? 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm assuming that you changed? Okay, so how many did I count? It's decreasing. 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 votes. Your friend you're still voting for it? So that makes it 10. So how many say it's false? 1, 2, 3, 4, 5. Are you voting or just holding? No, 5. Only 5. Okay, so fortunately or unfortunately, I think more fortunate the way the world is going, things in science is not decided by majority. But so those who say it's true has to give a proof. Your friend roughly outlined an idea of a proof. We have to write it down and check it. Those who say false should do what? Give a counterexample. So you have a counterexample in mind? Okay. Player 2 has? 2. Player 1 has 3 strategies. Good. Top, middle, bottom, left, right. So actually, we only care about player 1. Okay. Actually, I think this was an example we did in class, right? Okay. So T does not strictly dominate B. It doesn't even dominate B. M does not dominate B, but 1 over 2, 1 over 2, 0. This mixed strategy profile, okay, strictly dominates the pure strategy B. Do you all see it? Do you want me to write it down? Yep. Okay, so let's call this mu1 bar, because we had all the tildes and all that stuff. So what is mu1? Mu1 bar, mu2 equal to. Okay. So let's call this QL, QR. I don't care about the numbers that much now. So what is that? It's 3 times 1 over 2 QL. Okay, the probability that he's going to get the payoff 0, plus 0 times 1 over 2 QL, plus 0 times 1 over 2 QR, plus 3 times 1 over 2 QR. Right? So these went, so that's 3 over 2 QL plus QR, which is equal to 3 over 2, no matter what mu2 is. Okay? Well, okay, no matter what mu2 is. What is mu1 of B mu2? It's 1 times QL plus 1 times QR, which is equal to 1. no matter what mu2 is. 3 over 2 is bigger than 1, no matter what mu2 is. So for any mu2 in delta is 2, we have this inequality, which means that mu1 bar, that is the mixed strategy where T is played with 1 over 2 probability and mu is played with 1 over 2 probability, strictly dominates the pure strategy B. But neither T nor B dominates it. Okay? Actually, given what we have just proved a little earlier, I didn't even have to worry about this. I could have said, put L here. Okay. 3 times 1 over 2 plus 0 times 1 over 2 is bigger than 1. And then I could have put R here. Okay. So 0 times 1 over 2 plus 3 times 1 over 2 is bigger than 1. Okay. So I didn't have to check against mixed strategies. I could have just checked against pure strategies of the opponent. Okay. But in this case, it was easy, so that's how I did it. But we're not always that lucky. Because of that, the statement that was given in part A of question 1 is sometimes handy. In this case, it didn't matter much, but sometimes it does. Okay? So even though a pure strategy is not strictly dominated in the original game, it might be strictly dominated in the mixed extension game. Or it might not. We actually had examples for that. And actually, one of them, if you put 2 here, okay. Yep.
I know this is true, but my claim is there exists, for example, in our case, UI, T, mute.
Wait a minute. There exists what?
There exists another SI double prime for each UI, SI double prime, mu minus I is greater than SI.
So UI,
SI double prime,
SI double prime, mu minus I.
is greater than UI, SI.
Mu. This. But this says that SI double prime strictly dominates SI, both in the mixed extension game and hence in the pure strategy game, which we just showed that.
But in an S double prime, it will always exist for each mu minus I.
Oh, okay. So you mean is so then SI double prime. So
It's not.
for E mu minus I in well, I'll just write it like that. So for each mu minus I, there exists SI prime. Okay. So that is true. But how will you use that?
Then I'll have another mixed strategy, mu I double prime,
Uh-huh.
which mu I double prime of SI double prime, it will be mu I
Okay.
SI plus mu I
Okay.
SI double prime.
Uh-huh. And then you'll have keep having sequences of those. But then what will you do with that sequence? You see, the thing is, here, you know, eventually, where is it? We want to get to something like this. So you're probably going to try to sum these up. Okay? But then, you see, this SI double prime depends on mu minus I. And for some mu minus I, you might be getting the same SI double prime. So you cannot just sum them up and expect to get this. Summation of these will not give you this. It's not guaranteed. Okay? So when you have a statement like that, you cannot change the order of a universal and existential quantifier. Okay? This SI double prime will depend on mu minus I. Okay? So you moving from here to here will not be possible.
If I show that there exists mu I double prime for every mu minus I, then it's true.
Yes, that's what we want to show, but you cannot, from here, you cannot move there. That's a problem. So that's what we're going to get to, but yes.
Why SI double prime depends on mu minus I?
Well, First of all, the way your friend wrote the statement, okay, yeah. Okay. The way your friend wrote the statement, so whether the statement is true or false, that's a different story. But the way your friend wrote the statement, the universal quantifier comes before the existential quantifier, okay? So this will depend on that. So if I, for example, say, for every A real number, there exists a B real number such that A is less than B, okay? Will this B depend on A? So if A is 5, for example, B could be 6.3. But if A is 7, this B will not work anymore. The statement is true. So the B depends on A. Okay? Okay? In very rare cases, it might be the case that the B does not depend on A. In those cases, we can change the order. But then we need additional information. Just by looking at the statement, I cannot say, just by looking at this, I cannot say that the B does not depend on A. It depends on what you have here.
I guess I was confused because of the initial statement was be a strictly dominated strategy of page. The initial one.
Yeah.
So I guess I thought because of that line there exists I don't know SI that is not dependent on mu SI, but
Yeah, but that's what we initially thought your friend was saying. So if a pure strategy was strictly dominated in the mixed extension game, then it's dominated in the original game. But the example that your friend gave shows that that's not true. Actually, that was something that we already had talked about in class. Okay? So a strategy can be strictly dominated in the mixed extension game, but not dominated in the underlying game. Okay? So what we have to do is something else. Okay, so how would you proceed? So, well, we have to, yes, sir. Okay.
I will define a MUI double prime.
Okay.
So that I will take all the properties assigned inside MUI
Uh-huh.
and redistribute it accordingly based on MUI prime.
So your friend is saying, so let's try that. So let mu I double prime be such that mu I have to be, so unfortunately I used SI to denote the special strategy. So I should use something else here for any SI tilde is equal to what? Mu I. So that's mu I double prime. That's what we're defining. If SI tilde is equal to SI, then what do you want? This mu I prime. Well, wait a minute. This is equal to mu I prime SI times something? Times mu I SI. So you're multiplying the two probabilities. Okay? Okay, otherwise? Mu I SI tilde plus mu I prime SI tilde. The whole thing? No, the times mu I SI. Okay? So far, so good? So far, so good? Any questions? Okay. So your friend claims that this mu I tilde is the mu I tilde that we're searching for. Everybody agree? Everybody agree? Well, first of all, for this to be the animal that we're looking for, it has to be an element of delta SI. That is, it has to be a probability measure over SI, right? Which means that if I sum this up over all pure strategies of agent I, it should be equal to 1. Okay? So when we sum them up, what do we get? We get summation mu I SI tilde plus mu I prime SI tilde mu I SI, where SI tilde is different than SI, plus mu I prime SI times mu I SI. So what is this animal equal to? We have to check. I'm not sure whether that sums up to 1. So that's what I'm trying to show. So we're summing this part. Okay. So the summation of all these will be, the summation of all those will be 1 minus mu I SI, right? So we sum up all these terms over all SI tilde different than SI. So the only thing missing in the summation from making it equal to 1 is mu I SI. So this part will be equal to this, plus we have this part that's a constant, take it out, mu I SI times 1 minus mu I SI. Okay, so far so good. Plus this term. So does that add up to? This is mu I prime, yes. That's mu I prime, that's mu I. We have to write better, otherwise we get confused. SI prime times mu I SI. So is that equal to 1? So that and that will cancel. That together with that will cancel. So you will get 1. So good. It adds up to 1. So it passed the first test. It passed this. So now we have to do this. Check for this. Okay? But the first thing you have to make sure that it is a probability measure. Okay? So then we check for so what is that animal equal to? What is that? What is the expected payoff of agent I when he plays mu I double prime and the opponents play mu minus I? Well, we just add those up. So it's going to be mu I prime SI times mu I SI times UI SI mu minus I. That's the part that comes from here. Plus summation SI tilde, I'll just write it shorthand, different than SI, of all that animal. Okay. Okay, so that's what we have. So let's try to simplify the terms. Okay, so actually if we, when Okay. If SI tilde is equal to SI, that's what we have. So we can write this as summation SI tilde over capital SI mu I prime SI tilde times mu I SI times UI SI tilde mu minus I plus, so that comes from this part together with this term, right? Okay, so that plus that, plus this part, plus summation mu I SI tilde UI SI tilde mu minus I, where SI tilde is different than SI. Okay, so what do we have? What can we do now? Any suggestions? So the first thing to notice might be this term does not depend on SI tilde, which the summation is taken over, right? So we can maybe take this out. If you take that out, what do you get? Mu I prime SI tilde times UI SI tilde mu minus I. That's equal to what? Expected utility that agent I gets when he plays mu I minus I. Okay? By the way, I don't know whether this is going to work. We're just trying. We took your friend's word. Plus this part. What will that be? Did I? Yeah, okay. Okay, so if we had SI in here, that's what who was talking? Okay, so your friend is saying take the summation over all SI, then subtract what you have, add it. That's a good approach, what we just did there. So that's the expected utility of agent I when he plays mu I and the opponents play mu minus I. And from that subtract mu I SI times UI SI mu minus I. Okay? So far so good? So far so good? So how do we know that this animal is bigger than? So this is what this is equal to. So how do we know that this is bigger than this? So what do we know? We already have this. So we can replace this with, so that's bigger than, well, we also know that mu I SI is, or do we have it? Mu I SI is positive. So if I'm going to say is bigger, I have to make sure that this term is positive. This term is positive. That's how we took mu I to be. So this thing is bigger than mu I SI times UI mu minus I. Where did that come from? I'm sorry. Where did that come from? It came from this statement. Okay? So this number is bigger than this number. If I multiply both sides with a positive term, it's still bigger. And then we still have the rest. Okay? So this term and this term are the same. They cancel out. And that's what we had. That's what we were looking for, right? And finishes the proof. Okay? Any questions? Yep.
What was our problem that said this exactly? How were you going to solve it? What was your...
Well, so whenever you see, usually universal statements are easier to handle than existential ones because, existential, so for universal, you just take an arbitrary mixed strategy, arbitrary element, and that's it. Existential, it's not arbitrary, it's something special. So my initial approach would be, well, do I already have something? Well, where did the SI is strictly dominated. So we know that there exists such a strategy. So I would try if this works, something which I already have in my hand, which I know dominates SI. So first I would have tried this. Then if it doesn't work, then I would check what was the reason that it didn't work and then fix it. But given that I already have the existence of some mixed strategy of player I, which doesn't exactly satisfy this statement from the outset, but it does something very close to it. Okay? So I would start with this and then work on that. So that would be my recommendation. Try if, unfortunately time is up, try if mu I prime satisfies the condition. So we have this. The only thing that I have to do is from mu I prime, I have to move to mu I double prime. Okay? So how will you do that? I'll leave that. Give it a try. Okay? But your friend's suggestion does work. But you have to make sure that the animal that you tried, you defined a function here, you have to make sure that they're all non-negative. Well, the non-negativity part was obvious. But if you had put a minus here, then we would have to check whether it's non-negative. Okay? Then you have to make sure that it adds up to 1. So it passes the first test. It's a probability measure. And then we do the rest, which is just simple algebra. But you have to be careful. Okay? Any questions? And that's it.